All right, so now we're going to talk about similar figures. So when I say that two things are similar, they're not exactly the same, or at least they're not necessarily exactly the same, but they're pretty close. So similar figures must be the same shape, but their sizes may be different. So I can make something bigger, but remember when we talked about scale factor, right? If I make one part of the dimension bigger, all of the dimensions have to get bigger. I'm not trying to just stretch something out one direction, okay? So if I took this original figure and I reduced it, that means I'm taking all of these sides and I'm making them smaller by the same scale factor to get this smaller octagon, okay? This little squiggly line symbol, this is the similarity symbol. This means that, well, this is the symbol we use for similar. So if I put octagon A, squiggly line, octagon B, that means that octagon A, or this blue octagon, is similar to this smaller octagon, or octagon B, okay? So it means that they're the same shape, but not necessarily the same size. Okay, there's a scale factor that relates this big one to this small one. So in terms of sizes, although the size of the two shapes can be different, the sizes of the two shapes must differ by a factor. That factor is our scale factor. So if I'm looking at this, if these are similar to each other, then their corresponding sides, remember that term, we talked about this in the last lesson, the corresponding sides have to be related to each other by a ratio, which is the scale factor. In this case, scale factor is 2. 2 times 2 is 4, 3 times 3 is 6, 3 times 3 is 6, and 3 times 2 is 6, 3 times 2 is 6, and 1 times 2 is 2. Enlargements. When you have a photo enlarged, you make a similar photograph. So in this case, if we multiplied the dimensions of the smaller photo by 3, we got a larger photo. Okay, notice how the rectangle kept its shape. Okay, it did not change, it did not stretch out. Everything is related by a scale factor of 3. Reduction, same thing. A photograph can be shrunk by a scale factor as well. So if I take this larger photo and I multiply it by a scale factor of 1/4, I get a smaller photo. So determine the length of the unknown side. In this case, I put a question mark. Most cases you'll have a variable here, like x, y, z, whatever, a, b, c. So solve for that missing side. What'd you get? You should have gotten 5. Let's look at this next one. Solve for this missing side. You should have gotten 12. Four times 6 is 24, so my scale factor is 6. 2 times 6 is 12. Sometimes the factors between two figures isn't as obvious, and some calculations have to be done. Okay, so if I'm looking at this, I've got 12, 15, and 18 versus 8, 10, and 12. Well, what's my scale factor? In this case, it's not a whole number, right? So how do I figure this out? Well, to do this, I need to figure out what my ratio is. Okay? What would I be multiplying 15 by to get 10? What would I be multiplying 12 by to get 8? And what would I be multiplying 18 by to get 12? So in this problem, what I would have to do is make a ratio. Compare the two sides that are similar to each other. Compare the two corresponding sides. So if I'm trying to get smaller, I'm going to take one of the smaller sides and I'm going to make a fraction by putting it over one of the larger sides, its corresponding side. So let's take, for example, 10 and put it over 15. Well, 10 over 15 can be reduced to what? They're both divisible by 5. 10 divided by 5 is 2. 15 divided by 5 is 3. So 2/3. Let's think about that. If I multiply 15 by 2/3, 15 times 2 is 30, divided by 3 is 10. 12 times 2/3. 12 times 2 is 24. 24 divided by 3 is 8. 18 times 2/3. 18 times 2 is 36. And 36 divided by 3 is 12. So the scale factor going from left to right is 2/3. And I know it's 2/3 because it's getting smaller. If I messed up my ratio and instead of putting 10 over 15, I did 15 over 10, well, 15 over 10 isn't 2/3, it's 3 halves, right? 15 over 10 reduces to 3 over 2. But 3 over 2, is that less than 1 or greater than 1? It's greater than 1. So that's actually the scale factor going from right to left if I was going the opposite direction. Talked about this the other day as well, or in the last lesson. When changing the size of a figure, will the angles of the figure also change? If I multiply this first figure by a scale factor, is it going to change the angles? You should already know this, but in case you don't, no, they don't. In this example, these are both triangles. Triangles have to have their angles add up to 180. Okay? These angles already add up to 180. So whether this is a larger triangle or a smaller triangle, the angles have to be the same as long as they're similar. We can verify this by placing the smaller triangle inside of the larger triangle, like this. Oh, see? Or this. Yeah. There we go. So the 40s match and the 70s match as well. Now in this example, we have a triangle embedded in another triangle. Notice how there's this large triangle right here. It goes from up there to down to this corner, all the way over to this corner. And then it connects back up here. Okay, so this large triangle versus this smaller bluer, I guess that's what this color is, bluish triangle. So this smaller triangle. So anytime you have a triangle inside of a triangle, they're automatically similar. Okay? In this case, I need to figure out what this missing side is right here. So in order to do that, the best way to do this is to break up the two triangles and look at each one separately. Look at the blue one separately, and then look at the bigger one separately. If I look at the big one, I've got a 30 by 40 by 50 triangle, and the smaller one is a 6 by 8. So how am I going to figure out what I have to do? Well, one way is see if there's a whole number scale factor that you can figure out. How would you get from 30 to 6? How would you get from 30 to 6? Or from 40 to 8? If I divide 30 by 6, I get 5. 40 divided by 8 is 5. So that means that whatever this side is, 50 divided by this side is going to give me 5. So 50 divided by 5 is 10. So this missing side has to be 10. So here I broke them apart to compare them better. I found out that the scale factor here is 5 going from the smaller one to the larger one, because 6 times 5 is 30, 8 times 5 is 40, so whatever this is times 5 has to give me 50. And I ended up getting 10. So you can use similarity to answer real-life questions as well. Suppose you wanted to find the height of this tree. You can measure the length of the tree's shadow. In this case, the tree's shadow is 10 feet. Then measure the length of your shadow. Let's say in this case, your shadow is 2 feet. If you know how tall you are, then you can actually determine how tall the tree is by making a proportion. So if you're 6 feet tall and your shadow is 2 feet, you can either compare your height to your shadow and create a proportion where you set that equal to the tree's height, which in this case would be a variable like x, to the tree's shadow, which is 10 feet. So if I did that, apparently I didn't write out the proportion. That's okay. If I did that, the tree ends up being 30 feet tall, because if I do 6 over 2 is equal to x over 10, which we're going to do, let's do this. Let's do this here. I'm going to take a quick pause. If I have 6 over 2, and I set that equal to x over 10, then I just need to look at, well, I have my two denominators. Is there a simple way for me to get from 2 to 10? Yeah, I multiply by 5. 2 times 5 is 10. Okay. So then that means that if I'm multiplying 2 by 5 to get 10, I have to multiply 6 by 5 to get x. And 6 times 5 equals 30. So x equals 30. If you want to see that a little clearer, we can do this. Let's do the equation. Let's make this larger. So if I did 6 over 2 and set that equal to x over 10. Because remember, this is your height, this is your shadow. So we made a ratio of height to shadow, and we took the tree's height and put it over its shadow. So now I told you to compare the denominators. I have 2 and 10. Well, if these are equivalent fractions, to go from 2 to 10, I multiply by 5. And to go from 6 to x, I also have to multiply by 5. And 6 times 5 is 30. So the height of the tree is 30. All right. So again, the tree must be 30 feet tall. So similar figures work just like equivalent fractions. 30 over 66 equals 5 over 11. 30 times 1/6 gives me 5. 66 times 1/6 gives me 11. Or if I went the opposite direction, 5 times 6 gives me 30. 11 times 6 gives me 66. Okay. Just discuss this. Scale factors of perimeter and area. So I'm going to discuss this, and then I'm going to give you a very short video to look at where I actually write all this out and give you solid examples. So this says that the scale factor of perimeter and area. perimeter is the ratio of the perimeters, for perimeter, the ratio of the perimeters is the same as the ratio of the sides. The scale factor is the same too. So what does this mean? This means that if I have the scale factor of my sides, that my perimeters change the same way. So if my scale factor of my sides is 5, and the scale factor of my perimeters is also 5. Area is a little different though. This says if the scale factor of the sides of two similar polygons is m over n. So you can call it any number, okay? In this case, we made a fraction. Let's say that your scale factor is 1/2. Then the ratio of the areas is 1/2 squared, or m over n squared, or whatever your scale factor of your sides was, squared. You square each part of the ratio. So if the ratio of your sides is 3/4, then to get the ratio of your area, you have to square that. 3 times 3 is 9. 4 times 4 is 16. So your ratio of your area is 9/16. And I'm going to give you a little supplementary video for this, okay? So don't worry about whether or not this clicked yet. That's it for similarity right now. If you have any questions, please let me know and we can discuss this, okay?